To understand what the temperature profile looks like in these internal flow problems, we need some representation or model, and this model is in fact the energy equation. So to sort of put us back into some idea of what we're trying to do, we understand that we have a tube or pipe for which we know the temperature, we know the velocity distribution is parabolic, so this is a fully developed flow. And we're interested in understanding what the temperature profile looks like within this pipe or tube, subject to different types of boundary conditions. And so the typical boundary conditions that are used for problems of this type, at least in terms of development of the analysis, are either prescribed temperature or prescribed heat flux. To first of all be able to understand the temperature profile, we need to think about how that profile is defined and where it comes from. So what I'm showing here in this blue highlight is a region of this flow, and imagine that what we're looking at, is we've talked about this before, is some region of the flow that is in some annulus So we're looking at a slice of flow that is at some distance r. So this distance from the center line is r. So you imagine again that the center line of this flow system is like this. This dimension is r. And we're interested in what flows in and what flows out of this control volume. And we perform an energy balance on that. And so at the x face, so let's make sure that's clear. So this is the x, and this is the x plus delta x location. We have an enthalpy flow in, rho u Cp T times 2 pi r delta r. That 2 pi r delta r is going to be the area that is associated with this flow. So cross-hatching it here, it's this region here, and there's a conductive, so this is a bulk flow energy transport. Then we have a conductive transport through that same face. Of course, it's the same area, and you see minus k dt dx, which is the conductive heat flux. We have at the x plus delta x face the outgoing convective enthalpy transport and the outgoing heat transfer rate by conduction. By virtue of the fact that this is a fully developed velocity profile, we know that u is only a function of r and the v component is equal to 0. So there is no convection in this radial direction, but there is, of course, conduction in the radial direction. And so again, we see the heat flux minus k dt dr multiplying this area element 2 pi r delta x. That 2 pi r delta x is this interior surface area. Again, it's 2 pi r, which is the perimeter of this control volume, times delta x, which is that thickness. And of course we have the same conductive type term at r plus delta r. What we see here is we see the transport out minus the transport in. And so we have that in terms of, in this location, minus k dt dr, again, in minus out. So we really have sort of modified this definition. We have in minus out is equal to 0 because it's considered steady. Normally, we would say that in minus out is equal to some sort of storage minus generation. but there is no generation, there is no storage, it's steady. So in minus out is equal to 0. You can think about it, the sum of the ins is equal to the sum of the outs. We rearrange and divide through by 2 pi delta r delta x. And as you can see, we start identifying pieces of this that we want to use a limiting process for. So we do the limiting process to get the definition of a derivative. We get our final value or final version of the energy equation for this fully developed pipe flow problem. And we can rearrange it and introduce the thermal diffusivity. So it would be worthwhile if you follow along and recognize that we're dividing through here by rho CPR. The K over rho CP is alpha, and then the R goes into the denominator. That R is lost in the d squared t dx squared term, and again we have alpha there. So it's important to note that we can substitute our velocity distribution in because it's fully developed. And so this is the general differential equation that one would solve to understand what the temperature profile is. But there's simplifications that can be made for this equation depending on different characteristic values of the velocity, the thermal conductivity, the length of the pipe, and the diameter of the pipe. So to really understand this, we do dimensional analysis, and by dimensional analysis we really mean that we're going to non-dimensionalize the different parts of this problem and understand what the physics might tell us from that process. So we haven't changed much in the way of our underlying energy equation. So this is our energy equation. Let's just make sure we understand what the different terms mean. So the first term here is the energy transport by bulk flow. This first term on the right here is the conductive energy transport in the radial direction. And the last term is our conductive transfer in the axial direction, or x direction. So if we non-dimensionalize temperature, length, and diameter, we non-dimensionalize the temperature. We first of all subtract off the wall temperature, and then we divide by the initial or inlet temperature minus the wall temperature. As you can see, theta then will be between 0 and 1. We have a pipe of a certain length, or a tube of a certain length, and we non-dimensionalize the axial coordinate x by the total length of the tube or pipe, L. So z, again, is also between 0 and 1. Similarly, s, which represents the radial coordinate, is between 0 and 1, and it's non-dimensionalized by the pipe radius. You can easily show by substituting these parameters into the differential equation we have above here that we get something that looks very similar but with coefficients. And so the coefficients that we get out of this problem are things like alpha over r squared, alpha over L squared, and we get a modification here, this 2UB over L. It's worth rearranging this a little bit more, and all we're really doing is we're dividing through by this 2UB over L. In doing so, we're going to identify a term over here well, it's really the term that is particularly important is alpha divided by UB times the diameter. And it shows up, we're going to rearrange a term that's associated with even the axial term in terms of this parameter. So I'm going to point out that there is there's a non-dimensional parameter in convection analysis that's called the Peclet number, PE, and for this particular problem, it's UB times the characteristic length scale. In this case, the characteristic length scale is the diameter divided by the thermal diffusivity. And so this thing is again called the Peclet number. And the Peclet number tells us about the relative importance of heat transfer by bulk fluid motion as compared to heat transfer by diffusive processes. So the numerator represents, because of the velocity there, and compared to heat transfer, we'll use HT by conduction or diffusion, because conduction is a diffusive process. So alpha represents, it's really this alpha over D. And so alpha over D represents, in a really weird way, some sort of velocity associated with thermal diffusion as compared to U, which is the physical velocity. So just let me point out how that might make sense. So alpha over D, I'm going to say, is like a diffusion velocity. And the way you can sort of see that is that alpha has units of meters squared per second. I mean, you know that this has to be non-dimensional. And of course, D has dimensions of meters, so alpha over D has units of velocity. So this non-dimensional equation has this Peclet number, as we mentioned, but it also has a geometric length scales. It has this L over R, or its reciprocal R over L. So those are the two things that really identify what are the important parameters in this equation. So we can use this idea of the Peclet number and this geometric parameter to really help us understand what's going on in this problem. So we think about three different cases. Geometrically, we can think about cases where L, which is the length scale of the tube, as compared to R, which is the radius of the tube. We can look at different cases for this. We can look at L over R that is about equal to 1 as compared to conditions where L over R would be small, or conditions where L over R might be large. So these are getting towards cases that might be of interest. And we want to see if our intuition about the flow in these problems is consistent with what the interpretation is by looking at this non-dimensional equation. So from the perspective of the non-dimensional equation, there are going to be things that strike us. For example, and we just throw this out as a case in point, and I'm going to just actually write this, I'm going to point out that the coefficients, so the coefficients of a non-dimensional equation give us an indication of the importance of the physics associated with the term that they modify. So let's write that down. So write it up here. Coefficients of a non-dimensional equation provide insight into the relative importance of the physics of the term that they correspond to. And maybe I should say the magnitude of the coefficient. So, and in fact, it's the relative magnitude. So let's just put that up here. The relative magnitudes of coefficients of a non-dimensional equation provide insight into the relative importance of the physics of the terms that they correspond to. So, what I mean by that is the coefficient of this term d theta dz. So the term d theta dz times this 1 minus s squared, the physics of that term are bulk fluid flow. The physics of this term, this 1 over s d ds s d theta ds, correspond to conduction in the radial direction. The physics of this term correspond to conduction in the x direction. So, when we say that the coefficient here, there's actually a 1 that's the coefficient here. When we say that this coefficient is 1, we're comparing that coefficient for the convection in the x direction with the coefficients associated with conduction in the r direction, which is 1 over Peclet L over r, and with the coefficient of the conduction in the x direction term, which is 1 over Peclet r over L. So if the Peclet number is, for example, large, which corresponds to a fast flow, and if r is smaller than L, it immediately tells us that the coefficient here, 1 over Peclet r over L, is very small. And it says that the physics of conduction in the x direction would be very much unimportant for a fast flow in a small tube relative to the length of the tube. And you'll see that that's an important approximation that we will make in these types of systems. So just to quickly move through this, when L over R is small, so it's the geometry is shown here. What this corresponds to is we can think about a couple of different problems. We can think about a problem where the Peclet number is small. So a small Peclet number means that it's really just a conduction problem. By modifying this problem, we just multiplied by Peclet RE by Peclet L over R. So we're multiplying by the coefficient of this guy. We're going to make the d squared theta dz coefficient equal to 1. So now this is 1 times d squared theta dz squared. It says that Peclet L over R, if that's small, then it says that the physics associated with almost all these other terms are relatively small. It certainly tells us that we don't have to worry about the convection term or physics associated with convection. It's a little bit more complicated in terms of what the implication is with respect to the radial conduction term. In general, the radial conduction term would be there, but it is not an important issue for other cases, and it all depends on what the overall temperature gradients in the problem are. What do we expect as far as the Peclet number large for this problem? It says that, and if you think about it, if you came into a shallow pipe or pipe of relatively small length, you expect that if the temperature initially coming in is 100 degrees C, that it's pretty much 100 degrees C going out, even if the temperature at the wall is 20 degrees C. So what it says is that almost all the other terms are relatively unimportant. So it says that this is an unimportant term, and this is an unimportant term for the most part. And so it says that essentially d theta dz is about 0, or theta is constant. So it says that what you put in is what you're going to get out. More typical in terms of the types of problems that we're going to deal with are problems where L over R is large and the Peclet number is large. So it's actually this case here. The Peclet number small case is sort of a weird case, and it says that over most of the length the temperature is near the wall temperature except at a point where the radial second derivative is almost 0. So it's not, that's a less important and interesting case than what we normally work with. So the case that we normally deal with is L over R large, Peclet number large. as we've pointed out before, the conduction terms in the axial direction are very small, and it says that so we look at the coefficient of the convection term. The convection term coefficient is 1, so that's fine. But what it says is that convection and diffusion are equal. So we look at the coefficient of this term. It says that convection and diffusion are important as long as L over R is comparable to the Peclet number, but diffusion actually becomes more important than convection if L over R is greater than than the actual Peclet number. So you think about it this way. You have a Peclet number. Maybe the Peclet number is 200. And it says that as long as L over R is about as big as 200, then, or said differently, maybe this should be really, as long as L over R is smaller than, say, 200, then I need to take into account both the convection term and this diffusion term. But at some point, when L over R is much larger than that Peclet number, all of a sudden, I really don't even have to worry about the convection term, and it's really just a diffusion term. It's really almost a conduction term, a conduction problem in the radial direction. You'll see that part of this is hinting at what it means to be fully developed in the thermal sense. And fully developed in the thermal sense is a suggestion that the temperature shape, that the profile of the temperature profile in a non-dimensional sense is unchanging. So this is again a fully developed, I'm going to say hinting at fully developed thermal profile. Okay, so at least we have some intuition about what the issues are in these types of problems, and the next steps really would be to understand how to solve problems of this type.